Forgive me while I get set up. All right, can you guys hear me today? Can I get a thumbs up or something?
Yes,
I can hear you fine.
Excellent.
Yeah,
Okay. All right. So I changed a lot of my settings yesterday because I was having a Zoom meeting with my kids who live far away. So that was fun, but now everything is messed up on my screen. So I'm trying to get it set back up for classroom mode. All right, so already you guys are noticing that there's been a change in how you get started for the day. That was not me, that's the math department or somebody set it up so that now you're thrown into a waiting room. Is that correct? I don't know much about that except that it was done to prevent Zoom bombing by outsiders that didn't belong in the class. So I thought there was a way for me to override it once the thing got started. Maybe I do have. I know here. Maybe that'll work. All right. Well, there's the possibility that now the waiting room is turned off for this meeting. Anyway, if that happens again, just be patient, and I'll try to admit you if I don't know, somehow if you have to get my attention, I don't know what to do. All right, so I sent you guys an email with updates and some thoughts that came after we met last time. Did you guys have any questions about that? Anything that I need to clarify? No? Everybody's good? All right, let me say, oh yeah, go ahead, Enrique.
So it said on there that you're going to be posting the videos on a YouTube channel, correct?
Yes, they should be already there.
Okay. Typically, how soon should we expect the recordings to go up after the class?
You're probably going to give me 24 hours.
Okay, thank you. That's all my questions.
Let me just tell you guys, it's weird. I don't know how it happens. I have the thing, I have Zoom set up so that it'll record these things automatically, and it does so. But then as soon as the meeting is over, Zoom comes up with a little pop-up window, and it says, it's processing this video, and it takes like an hour to process it. I don't know what kind of processing it's doing, but it eventually creates this MP4. Oh, I gotta silence my clock, hang on. Sorry, my guests always complain. Every 15 minutes, that thing makes a lot of noise. Anyway, then I have this half a gigabyte file, which has to be uploaded to YouTube. And since I do that for 3 classes, it can take me kind of a long time to get all the processing done. All right, another thing I have to clarify is the homework. So you guys have a homework that was due last night, and then I changed it so it's due tonight. And I've had a couple of people ask me for help on that because I guess some of the questions don't seem like they flow very easily from what we've talked about so far. So if you guys want to suggest 1 or 2 questions from the homework that's due tonight, we can do that one together. And then I'll get started on the new material, which is part of the next homework, which is already up. I've gotten a couple of emails where people pointed out that I may have mixed up which homework set should go with which week because now our schedules are all off. So if you are starting the next homework that's due, it says it's due on the 8th, go ahead and do the problems that you can do, and the ones that seem kind of mysterious, hold off on those because I may have to either remove them from this homework set or just extend the deadline to maybe it'll be at the end of next week or something. Okay, so anybody want to ask me about the homework that's due tonight? No? Everybody's good? Cool. All right, well, when we last left our heroes, we were talking about Fubini's theorem and how it allows us to compute integrals over rectangles. Rectangles are the easy case. We will in general have to integrate functions of more than one variable over regions that are not just rectangles. So it is possible to use Fubini's theorem to do that, but you have to set everything up appropriately. So let me swing my camera around. Oops, how did I do that last time? Oh, hey, can I just make a little comment? In order to get this little camera to move around like this, what I did was I took a swing arm lamp and I put my camera at the end of it so that it allows me to move this thing in many different directions. That's actually an example of dimensions and dimension counting, just like we've talked about a few times in this course. This little lamp has a total of, I think it's 6 or 7 hinges, each one of which allows 1 degree of freedom in motion. In other words, you can tell exactly how the lamp is configured by measuring the angles that I've twisted it at 6 or 7, I think it's 7 different locations. So to specify exactly how the lamp looks, what you end up with is a total of 7 measurements. So the input to the problem I'm about to describe, it's going to be a set of 7 variables. Just to show you, it's this kind of a lamp. I can't, the camera's on it, so I can't swing it around. And it's attached to my desk here. So it can rotate in this direction right at this axis, and then here there's another hinge and it rotates in the perpendicular direction and so on. So you would specify exactly how this thing is oriented by giving me those 7 different numbers, which is to say that each position can be thought of as a point in 7-dimensional space. From that, you could determine exactly how the camera is going to be presenting things to you guys. So what you would want to know is, first of all, what is the location of that dot that's at the center of my camera? And that would be a position in 3-dimensional space. So that gives me 3 output variables. And 2 other things that you would want to know is, even after you've decided where this like center of mass is, you should imagine a sphere that wraps around this, and then ask yourself, where would the line of sight of the camera be piercing this sphere, which you would measure by giving both a latitude and a longitude, which would be 2 numbers, that's a point in R2. And then furthermore, once you've decided exactly where the center of the camera is and what part of the globe it's pointing to, then there's one more thing that you could do, which would be to twist it around, like if I do this to the camera, I'm making the image rotate, even though I'm pointing it to the exact same spot on the globe, and I haven't moved the center of mass. So there's one more thing to measure, which is the amount of rotation of the image, which is a real number. So I can play with the camera on its mount to change 7 different variables. And then what I can measure from that is a total of 6 different things: 3 coordinates for position, 2 for orientation of the this line, and that vector, you can think of this as a vector in R3. And finally, 1 degree of rotation around that vector. So what you actually get is that the manipulation of the camera gives me a function that goes from R7 into R6. You change any combination of those 7 angles of the lamp arm, and what it'll do is it'll change all 6 of these different numbers. what makes it possible for me, or the reason that I rigged it up with this lamp, is that I need for this number here to be at least as big as this number, because you should expect in general that if you have a function that goes from a lower dimensional set to a higher dimensional set, that you can't get every point of the higher dimensional set. If I had a lamp with only, let's say, 4 different things to manipulate, then I might still want to measure the 6 different output things. But since 4 is less than 6, I can't expect that I would be able to get all combinations of the 6 variables with only 4 things to play with. In engineering terms, you think of that as having only 4 degrees of freedom when you want to have 6. And mathematically, the statement is that you have a function from a lower dimensional space to a higher dimensional space, which can't be what we say is onto. It can't be a surjection. You can't get every point in this space, even if you use all the points in this space. So if you had this, this would be not possible to get every point. We have had situations like this where I take a function that goes from R1 into R3, and that the context for that would usually be a parameterization of a curve sitting inside 3-dimensional space. Well, you know, a single curve doesn't cover every point in 3-dimensional space. It only covers, well, a curve. So, I mean, on a practical level, you just might think, oh, I got a lamp that can swing around in a lot of different ways. But the key thing is you need to have 6 degrees of freedom in your swing arm lamp if you want to be able to make the camera do every possible motion around in space. Like that. Okay, so there, that entertained me. I don't know if you guys care. All right, so somebody had a question on homework. Problem number 7 in the homework. I don't remember what the question is. Let me see if I can pull that up real fast. Exit full screen. Where's the thing? Problem 7. Oh, yeah. That's the one where we're building up this 3-dimensional shape. Oh, wrong thing. Let's do that. There we go. All right, so each of you might have slightly different numbers. I don't remember if this is one of the problems that gets randomized a little bit. But here's the picture. Somebody has constructed a 3-dimensional shape by drawing a parabola in the XY plane. So here's the x-axis, here's the y-axis, and then there's the parabola is the set of points where y is equal to x squared. And implicitly, they're saying that z is equal to 0. So 2 equations in the 3 variables, x, y, and z. That should be 3 minus 2 is 1, so that's a 1-dimensional set, which is a curve. All right, and then they construct above this a funny-looking shape. I don't have a name for that shape. I can't even tell you something that I can think of that looks that way. But what they did is, at each point in the along the y-axis, they drew an equilateral triangle that stood up perpendicular from the xy plane, but stretched out from the parabola to the parabola. So you have smaller triangles on this end and larger ones on this end, and you put them all together and you get a 3-dimensional shape. For those people who can't visualize 3D things so well, can anybody suggest something that looks this way? I can't even imagine what that would be. It kind of looks like a turtle shell or something. Half a turtle shell. The head would be over here. Feet.
Looks like the Sydney Opera House.
Oh, okay. Yeah,
Thanks.
the Sydney Opera House. Yeah, okay. I think that's better than the turtle.
Thank you.
Okay, so the question is, what is the volume of this? And the real question is, how does this turn into an integration problem? So the thing you need to remember from last time, and you need to remember this about integration in general, is that what an integral represents is it's a limit in a certain sense of taking a sum of products And by the products, what I mean for you to be doing is you want to take the size of a piece of the set S and multiply that by the value of some function, so value of the function f at a point within each one of those pieces. So we have to think of something that we're going to split up into a lot of parts, and some function that's going to be defined at each point in that set. And then think of a way to decompose that big set into smaller pieces in such a way that this product has something to do with calculating the volume. And the way that works for this problem is, I would say, to let S be the interval on the on the y-axis that goes from y equals 0 to, I don't remember what the right-hand edge was supposed to be. Was it y equal 5? That's the way it looked in my version of the problem. So that's going to be my set S, is I'm going to take the interval from y equals 0 to y equals 5 along the y-axis.
Dr. Rusin, could you angle the camera up a little bit so we can see your page better?
Yes. Oh, yeah.
Right there, perfect.
Yeah, thank you. Or twist the paper. Yeah. Okay. All right, so what would I get out of splitting this set S up into little pieces? If you do that, then this interval from 0 to 5 can now be broken into a few smaller intervals. The size of each one of these pieces would naturally be interpreted as the length or the width of that piece of the y-axis. So why would I want to be measuring, multiplying the width of a little interval on the y-axis by anything? And the answer is that if you think about the way they've built this shape, you can think of the shape as being the union of a bunch of solid three-dimensional triangles that are equilateral on both faces, but they have a little bit of a width. Because if you multiply the width of such a figure by the area on each end, then what you'll get is the volume of that. That's a principle that we've used before, is that in general, if you take any set in the plane and then stretch it out or extrude it straight up into three-dimensional space, then the volume of such a figure will always be equal to the area on the bottom or the top or any cross-sectional area, they should be all the same, times the height. So I think we've mentioned this on the days when I wore my pizza shirt that showed the volume of a cylinder as being, the volume of a round cylinder would be pi r squared h. The pi r squared is the area on the bottom, the h is the overall height. So I'm using this in the case, in our figure, if you want to get the volume of a shape that looks like a prism, that's an equilateral triangle on both ends, but a little bit thick, then the volume of this would be equal to the area on the face times, well, this height right here, which I've turned it sideways from the previous picture. The thing that I'm calling the height in this description is the thing that I was calling the width, which is the width of that little interval where it crosses the y-axis. So I'll write it here as being the area times the width. Now you do have to realize that the shape that we started with isn't exactly the kind of picture that I just created, because in everything that I was doing here, I was assuming that the top and the bottom were congruent geometric figures, so that in particular the area on the top and the area on the bottom would be the same. In reality, in this figure, the sizes of those triangles is increasing a little bit as you move from left to right. The triangle in the 3D thing that I've shown here, the triangle on the left face has got a little bit bigger area than the one on the right face. But we can estimate this, even though the sides are a little bit slanted. Let me try to draw it with a slight slant to it. Even if you had a slightly different triangle on the top than you did on the bottom, so now it looks like a truncated pyramid, you could either think of this as being approximately the area on the bottom times the width, or you could say it's the same as taking the area right in the middle somewhere. There's got to be a magic spot, a magic height right in the middle where the cross-section is bigger than it is on the top, but smaller than it is on the bottom. And if you choose just the right point, you get exactly the right area. Whichever way you want to think about it, if you use this kind of a formula in this setting, then multiplying this, if I take this function f to be the function that dictates exactly what is the area of that triangular face at a particular point on the y-axis, that's going to be a function of y. It's going to increase from an area of 0 when y is 0 to some big area when y is 5. But it'll always be a function of y. And if I keep evaluating that function at different points along this y-axis, and I multiply all of the values of that, all of the areas of those triangles, by the sizes of these pieces of the y-axis, then what I'll be computing in every one of these spots is exactly the volume of one of these little slices of my original shape. If I then go to add all of those volumes of the slices, I'll get the volume of the whole thing. And so that leads me to the following formula that says that you will get the volume of the whole figure, and it's the volume of the Sydney Opera House here, or my little turtle back. The volume of the whole thing is now written as the integral across this interval, and we're integrating with respect to y. We're chopping up the y-axis into little bits. And the function that we're supposed to integrate is the function of y that tells us what is the area of the triangle at a given y coordinate. And I'll just pause here for a second to say that this is exactly the way that you can compute the volumes of pretty random three-dimensional shapes. Take any three-dimensional shape, pick a line that goes through it, any direction, I don't care which axis you use, and then you can get the total volume by adding up the volumes of the little slices that are taken perpendicular to the line that you just drew. Then you let S be that line segment of the portion of the line that actually pierces your figure. You imagine splitting that line segment up into a bunch of little pieces, and you keep multiplying the widths of the pieces times the function that tells you the area at a particular spot in the cross-section. So we can do this in a lot of shapes. I think I have more for you in future homeworks as well. They'll probably show up on the tests.
Dr. Rusin?
Yeah.
Why did you change S from 0 to 5 to 3 to 5?
Oh, I'm sorry, I don't know why. It should be a 0.
Okay.
Thank you. Oh, yeah,
Thank you.
I think it's because last time, didn't I do an example that had 3 to 5 in it? I don't remember. All right, so the only thing that's missing in our calculation, all of this is very general, and it gets to the heart of exactly what integration is. So I want to make sure that you guys understand this. It's the setting up of the problem that's key. To get the idea that when you write down an integral, what you're really computing is one of these limits, meaning it's a limit as the pieces get tinier. It's a limit of the sum of a bunch of products, where in the product, one of these things can be any weird kind of a function. I haven't even said what that is yet. But the other factor in this product is always something that measures the size of the piece in your decomposition. So now to return to the specific problem, where you're going to have to actually start to do some work instead of just conceptual stuff, is you now have to figure out how to calculate the area of the triangle that results from going to the original 3D picture and slicing it perpendicular to the y-axis, and then looking at the area of the figure that results. So if I can change your view now, I'm going to walk over to the positive y-axis and look back. Here's what I'm going to see. I'll be standing on the y-axis, and here's me sort of standing in front of the big triangle. And I need to know what is the area of the triangle that I have when I know exactly what is the point on the y-axis that I'm standing at. Now, that can be a little tricky in some cases. What I've encouraged students to do when you get stuck is to look at a few extreme cases first. So for example, what if I ask you for the area of the triangle that you get when the y coordinate is 0? What's the area that you would get for the triangle that results from intersecting this three-dimensional shape perpendicular to the y-axis, but at a y coordinate of 0? What's the area in that case? Somebody must know it. No takers?
0?
That's 0, yeah. When you're all the way at the edge, then the slice that touches right here is not going to give you any area at all. It's the triangles have been reduced to nothingness down at that edge. It's maybe a little, it's less obvious, but we can stare at it a little better. What about when we're here all the way at y equals 5? Well, for that one, then we have to put in some more pieces of information on this figure. If you took the slice through the point where y is equal to 5, then there would be some very specific coordinates that I could write down for what are these 2 points that are at the corners of this triangle. Obviously, there's a third point as well. But what are the coordinates for these 2 points? They both have z equal to 0, obviously. And what else do we know about the coordinates of these 2 points? Nobody wants to chime in. They both are lying on this. If I say I want the one that's all the way at the right-hand edge, then they have a y coordinate of 5. So I would put 5 in as their y coordinates. How about the x coordinates? What do I know about the x coordinates of these 2 points? Where am I going to get that information from?
Isn't the x coordinates just square root 5 plus, isn't it plus or minus square root 5?
Yes, exactly. Because the one other piece of information we know about these points is that they do lie on the parabola where y is equal to x squared. So that tells us that the x coordinate of one of them is the square root of 5, and the x coordinate of the other one, I didn't leave myself enough space here, that's the negative of the square root of 5. So just so that you can see where I did this, I stared at these 2 points that became 2 of the corners of my triangle, and I asked myself what I knew about them, and I knew 3 things about them. I knew that they were in the xy plane, I knew that I was looking at the right-hand edge of the figure, and I knew that the 2 points were both on the parabola. So now you see 3 equations, sorry, the equal sign is gone here. Now you see 3 equations that link the 3 variables. 3 equations, 3 variables, you should be able to get the coordinates of the solution. And sure enough, this is what we found. We've got the coordinates for each of those 2 points. The reason that I wanted those coordinates is that once you know the coordinates of the points, you can figure out the length of this line segment that goes across the bottom. That length of that line segment is exactly the distance between those 2 points. And well, 2 points in 3-dimensional space, you could use the distance formula to get the distance between them. But since they have the same z coordinate and the same y coordinate, the distance between them is just the difference of their x coordinates. And so now I know the length of this edge of the triangle. It just comes out to be exactly twice the square root of 5. And getting that length is kind of an important step, because what I'm asking you for here is the area of the triangle. If you know the side of the triangle, how do you get the area of the triangle? Remember the formula for the area of an equilateral triangle when you know the length of the side?
Isn't it like root 3/4 times the length of the side squared?
Mm-hmm. Yeah, just on dimensional grounds, you know that it has to be L squared times a number, right? If this is measured in centimeters, this would be square centimeters, which is what you want for an area. So the only thing to figure out is exactly what is this multiplier, and yeah, it's square root of 3/4. At least I think that's true. Isn't that true? Square root of 3/4, I'm pretty sure, is the right number. So that gives me something that I can put in here for what is the area of the biggest triangle, the one that's furthest to the right in my figure. And I get it by taking root 3/4 times this number squared. When you square this, you'll get 4 times 5. And of course the 4's cancel, and you have root 3 times the square root 3 times 5. Now, you didn't actually need to do that particular triangle, but I find it helpful to do that one, and maybe another one if you just want to warm up. Pick another value of y if it helps you to have actual numbers to stare at, but go through exactly the same routine and you'll figure out exactly what the area of that triangle would be. Obviously, if you slice this original 3D figure somewhere between the left edge, where y is 0, that's the x-axis is where y is 0, and the right edge, if I went to y equals 3 or 2 or 4.5 or whatever, then I would go through similar kinds of calculations and I would get a similar looking formula for the area. If you don't mind, I'm going to just jump right to the general case where the y coordinate, where I'm taking the slice, is just going to be called y. And if that's the case, then I just have to kind of change a few of the numbers in this little picture. These 2 points are still on the bottom of the triangle, so they still have a z coordinate of 0. Now I'm specifically choosing those points to have a y coordinate equal to some other number that I'm just going to call y. And then I just need to figure out the x coordinate, but I'm still bound by that one last equation that says y is equal to x squared, so x is one of the 2 square roots of y. I'll have the positive square root of y on this side and the negative square root of y on this side. So just exactly as I did this calculation, I discovered that the length of the bottom edge of the triangle that is formed at a particular y coordinate, that length is just twice the square root of y. And therefore the area of that particular triangle will be root 3 over 4 times the square of this, which is 4 times y. And just as in the previous line, oops, the 4's cancel. And I get a nice simple formula, the square root of 3 times y. And that allows me now finally to return to the integral calculation that was supposed to give me the area, give me the total volume. And it's now written as the integral over the interval from 0 to 5 of root 3y. That's replacing all this stuff in the giant parentheses times dy. And at this point, you can just grab any Calc 1 student and ask them to do the work for you. When they integrate this function across this interval, they probably think they're computing an area, but you don't have to tell them that that's actually computing the volume of something more interesting. They're going to write it this way, and they will calculate it using the fundamental theorem of calculus by finding an antiderivative, sticking in the endpoints, and then when they evaluate this, you get 25 halves times the square root of 3. With any luck, that's one of the answers that they offer to you. Is it? Actually, I don't even remember myself. Hang on. Oh, I had different numbers on the version of the problem.
Yeah, same here, so I'm not sure.
Yeah, in all of the versions that I've seen, the problem is always identical, except that this right-hand line segment is at different values of y. So if you were given a number in this spot, I think you can trace through that you just replace every one of the 5's in my calculations with that other number. And so if, for example, you had a 4 here, then your final answer would be root 3 times 16 halves, which is 8. So, yeah. So this does seem to, with that adjustment, this matches the answer that's given on the version of the problem that I have. All right, anybody need to ask me a question or clarification on that example? Because this is kind of important here. It's not so much that we need to be able to calculate volumes, although that gives me a handy source of problems to assign to you guys on a homework or a test. But I do need you to see that something like a volume calculation can be broken down as the total volume is the sum of a bunch of smaller volumes, and all of those smaller volumes are a very tiny width times a cross-sectional area. And so we always end up computing volumes by doing just this kind of a trick. How exactly you find those cross-sectional areas, that takes a little bit of geometry on the side. And then after you've figured out those cross-sectional areas, then you may have to do some integration on the side. But the part that's new for us in this course is just the focus on how the volume turns out to be an integral in the first place. So make sure you understand that part.
Dr. Uzen?
Yes, go ahead.
I had a question. So in this case, is the set that we're integrating over, is that just a line?
Yes, a line segment. It's the interval that goes from the left to the right edges of this figure. There are other ways that you could have attempted to describe this volume as an integral. It's just that I know from experience that in this particular problem, it wouldn't work out as easily. So you could, for example, have said that the volume that we were trying to calculate can be thought of as the integral of, I'll just write F for a second, and then the S would be this region in the XY plane that is surrounded by that parabola. So it's got y equals x squared as one of its edge curves, and the other edge curve was y equals 5. Those two curves in the XY plane surround this kind of thumbnail-shaped region. And if I do an area integral over that region, where the function f measures just how high the roof line of the opera house is at a particular point in the XY plane, that would also give me the volume. Just to clarify, what you're doing when somebody writes this kind of an integral down, let me finish writing this out, where f of x comma y is equal to the height of the roof at a particular point, x comma y. A person who writes this kind of an integral must have been thinking of the problem in the following way. They're going to write it as an integral by decomposing the shape in the following way. Here's the same picture that I had before. I'm trying to make it anyway. But a person who writes this integral is envisioning that you have this sort of completed building. So this is actually the framing of the building. It's got a bunch of straight girders that go along that edge and other girders on that edge. And then at each point in the XY plane, it's possible for you to just look up and calculate how high the roof is right there. And if you call that, I mean, that's something that's going to vary with the point, x comma y, so it's a function, f of x comma y. This is a function that's now defined on the xy plane, or a portion of the xy plane, and it spits out a real number at every one of them. So a person who writes this integral is saying, aha, I'm going to look at the floor plan of the Sydney Opera House, break it up into a bunch of little tiles, and then in every one of those little tiles, I'm going to choose a point, use this function f to measure how high the roof is at that point, build myself a skinny little tower that stretches all the way up to the roof right there, but I'll make it a blocky tower. So inevitably this little tower that I built, it's probably going to be projecting outwards off the side of the Sydney Opera House at some spots, but it'll be projecting to the inside of the building as well in other spots. It just exactly matches the height of the building at one point over that little tile. But it's not a bad approximation for how much volume of space there is directly above that tile. And when you add the contribution tile by tile, your little block towers will be of different heights. But collectively, they're going to give you the total volume. And or at least it's an approximation to the total volume, and the approximation will get better and better if you make your tiles smaller and smaller, because then these little errors off on the edges, they get to be more minuscule. So now how do you get the total volume? The total volume is the sum of the volumes of the little towers, and the volume of each tower is the area on the bottom times its height. Well, the area on the bottom, that's the thing that I keep writing this way, as the size of the piece. It's the size of a piece of this figure. Size in this case now means area. but you multiply the area on the bottom times the value of this function, and I wrote here that the function is just measuring the height of the roof. So you are calculating this volume now as an integral, but it's a different kind of integral from the way I did it. I split my shape up into a bunch of these thick triangles. This person is choosing to split it up as a bunch of blocky towers. So they're both valid, but they're going to end up giving you an integral that looks different. I wouldn't like this particular approach for this particular problem just because I don't really have a formula for this function f. I don't know how to calculate exactly what the height of the roof line would be.
Yeah, because I used this method and I wasn't able to find the formula.
Right. I mean, we could do it. I could sit here and try to do some geometry, but it would take me a long time. I'd have to say, well, if you know the y coordinate, then I can, as a sort of a side problem, I would be drawing this kind of a figure where I'm going to hold the y coordinate fixed, and so I'd start to draw this triangle, and then I would go to a particular point between the left and the right and say, okay, if I know my x coordinate, somewhere between this x coordinate and that x coordinate, if I take any other x coordinate, can I figure out how high that dot is? And the answer is yes, you could do it because there's a straight line here and you could find the slope and all that stuff, but that'd be a pain in the neck to do it that way. And I'll tell you one other way that you could have done this problem. Again, not a practical way for this particular problem, but it's a conceptual way. You could have taken this whole shape. Again, we're looking at the volume of the interior of the Sydney Opera House. But what's the set S that I'm going to decompose, and what function am I going to evaluate on each little piece? Well, you could have a person that just imagines these little towers, but they build those towers one empty Amazon box at a time. And now I'm imagining that the Sydney Opera House is being used as an Amazon warehouse. And so they're taking the set S to be the total interior space. And I'm decomposing all of that space into lots of little boxes. And the trick here is what you're going to do is you would get the total volume by saying, okay, the total volume of the whole space is the sum of the volumes of all of the little boxes. Well, how big is each little box? That's easy. You get the volume of each little box by taking the size of the box. Well, that can only mean the volume of the box. And you multiply that by 1. In other words, you don't really do anything except look at the size of the little box. That is not a practical thing to do, but it does allow me to write the total volume as an integral in a different way. The total volume is now the integral over the entire interior of the function 1. The function of 3 variables, it's 1 plus 0x plus 0y plus 0z, if you want to write it that way. It's that function of 3 variables. I keep evaluating that function over and over at different points inside this 3-dimensional space. So I'm taking the value of the function and I'm multiplying it by the size of a little piece of this giant set. Size in this case means volume. And the way, and therefore people would write the little differential notation at the end would probably be a dV. So this is a completely useless formula for us in this case. It doesn't really give us any calculational start, but it's a good principle to remember that if you want to get the volume of a set, think of that volume as being an integral over the entire set of the constant function 1. And that will turn out to be something that's actually useful after we get some more theorems under our belt. There will be some other things that we can do with that. Okay, so what I wanted you guys to get out of these last 2 giant words that say or is just to realize that the original problem, it was intended that you do it the way I was doing here in the green. But the principle of using integrals to get the value of something like a volume allows you to write this one calculation as an integral of many different types, either an integral over a portion of a real number line, or an integral over a portion of the plane, or an integral over a portion of three-dimensional space. Well, I really didn't want to spend all of my time on that one example, but I think it was probably time well spent. Now, let me get you guys started on the next section, which was using Fubini's theorem, even in cases where we don't have a rectangle to integrate over. And I think to save time, I'm going to use exactly that same region in the plane that we were using in the previous example, but I'll have a different function to integrate. So let me make up an example for you here, where S is exactly this region in the XY plane. Let me turn it around in kind of the usual way. So it's bounded by the curve y equals x squared and by the two lines y equals 0 and y equals 5. So this is a set S in two-dimensional space. And let's just make a function of a couple of variables that I'm going to integrate over that function, over that set. So let's just use 4xy plus 7x squared. How's that? Now make this a 6x squared. Okay, so what if I ask you for the integral of this function f over the set S integrated with respect to area? Conceptually, that means you're dividing this thing up into a bunch of little chunks, and you'll multiply the area of each chunk times the value of this function at some point inside that chunk. I'll let you draw the graph of this function. I think I sent you guys a link to some software that would help you draw the graph. Then you'd be looking at some kind of weird shape that floats above this region, and I'm asking you to, I don't know, calculate the volume of the shape that lies under the graph and over the set S. Setting the concepts aside to get the calculations, here's the way you're going to do it. You're going to say, it's a little cheat. You're going to say that to integrate over the set S, I'm actually integrating over a bigger set R, which is a rectangle. This is the same as integrating over the function, over the rectangle R that I just drew. So S is the shaded region, and R is this rectangle that includes that shaded region. But I have to have a slightly different function f. I don't want to use this formula all over the set, over the rest of the rectangle, capital R, because then I would be adding some additional volume in this region and that region. So what I want to do instead is to integrate a different function g, where the function g is the same as f when the point x comma y is in the set S, but outside of the set S, I just want you to make the function g be equal to 0. That's the only reason to do that is so that I can have an integral that's defined over a rectangle. And if I have an integral defined over a rectangle, then I get to use Fubini's theorem, which would say that I could write this as an integral where the y-coordinates go from 0 to 5, like you see in the picture, and the x-coordinates will go from, what did we say they are over here? Minus the square root of 5 to plus the square root of 5. But the function that I have to integrate is this function g. And my function for g looks kind of a mess. Fortunately, it's only a little bit of a mess because it's just saying, oh, well, the function g is going to be 0 for some of the points. In other words, the function g will be 0 whenever you have an x-coordinate that's too big, whenever you've stretched too far to the right of this edge or too far to the left of that edge. The only values of x that are really relevant are the values of x that keep us inside of this parabola. So in that case, I might as well throw away the other values of x. On this inner integral, the only x's that really matter are the ones that vary between the negative of the square root of y and the positive of the square root of y. Because like I say, the way I've set up my function g, it's going to be 0 for any other points, for any other values of x that you might stick in here. If the x's are more than this or less than that, then the value of the function g is 0. And once I've thrown those points away, for all the other points, x comma y, as long as the x-coordinate is fairly small, it's between that number and that number, then the function g is identical to the function f, so I get to use this formula. So just to pause here for a second, what you just saw me do was to take the original problem, which was an integral of the function f, and I wrote it as an iterated integral, and I just copied the formula for f in here, and I kept my outer limits of integration exactly the way you might have guessed from this picture. The y-coordinates do go from 0 to 5, but the change you have to make is to make sure that your inner limits of integration constrain you to the actual values of the x-coordinates that you're going to see in this picture when the y-coordinate has been held fixed. And just to help you remember that, what I asked you to do last time when we first talked about Fubini's theorem is, when you're performing this inner integral, you were going to treat x as a variable, all right, but everything that wasn't an x was being held as a constant. So you need to look at this figure and say, yes, well, if you do hold y constant, then what's your range of x's that you're going to see in this picture? And the x's won't go all the way from minus root 5 to plus root 5 if you're holding your y-coordinate fixed at some level. So just, if I should draw that picture again a little bit. If you stay within the interior of this region with a fixed y-coordinate, then the range of values of x's isn't going to go all the way from minus root 5 to plus root 5. It'll only go from minus the square root of y to plus the square root of y. So that's where I got those limits of integration. This is the part that trips students up. You have to draw this figure so that you can see what the new range of x's is going to be. Once you have that, all the rest of the calculations go pretty automatically. I know I've run over here, so I'll do this kind of fast, and we'll do it again next time. But so you guys can start practicing if you wish. To compute this integral with respect to x, I'll anti-differentiate with respect to x, treating everything that's not an x as a constant. There's my antiderivative. And I stick in these two values of x. Oops, equals the positive square root. And all of that stuff should make all of the x's go away. I'll have only a function of y inside the square brackets. Precisely what it'll be is 2x squared times the square root of y. I'm sorry, 2 times y, x squared will be equal to y, times y, plus 2 times the square root of y cubed. And when I stick in the other endpoint, what I'm going to get will again be 2y squared for the first part. And if x is the negative of the square root of y, then this will turn into negative twice y to the 3/2. So if you watch your minus signs carefully, you'll get cancellation on this part and addition in this part. And you should observe that at this moment, actually at this moment, all the x's are gone and you have only a function of y to integrate. And when you do integrate it, it's just the power rule. So this is the final value that I would get, and I'll let you get some number. Okay, I went over. I apologize for that. We'll do more examples of this next time, but it's getting these limits of integration that tends to be the hard part. So give it a shot and ask me some questions next time. Final comments? All
Could
right,
you
guys.
have done it? Oh, I have a question.
Oh, yes, go ahead, go ahead.
Could you have done x and then y, or?
Yes.
Wait.
Yes, there's nothing in this problem that forces you to put y's on the outside and x's on the inside. You can do them in either order. Fubini's theorem is flexible that way. You absolutely have the right to do it in either direction. And I will tell you that there are plenty of examples where the problem is much easier if you do it in one direction than the other. In fact, it's a common problem, and I'll do some examples with you guys on a future date. It's a very common thing for me to write down a double integral just like this and ask you to kind of get things reversed. And it's a little more complicated than just simply moving these sets of symbols because you got to draw a picture. So, good question. How about if we attack it next time?
All right, thank you.
Thank you. Thank you all, guys, and I'll see you in 48 hours.